Hello everyone, I am Rekha Murthy, Assistant Professor from EEE Department from Sai Vidya Institute of Technology. I am here to present the cycle of experiments which is involved in Electrical Machine 1 laboratory. So let me explain about the list of experiments which are there in this laboratory. So this laboratory is for a third semester. The title of experiments is the first experiment is open circuit and short circuit test on a single phase, step up or a step down transformer, and predetermination of the efficiency and regulation, and as well as the calculation of parameters of equivalent circuit. The second experiment is related with the sumpness test on a similar transformers and determination of combined and individual transformer efficiency. The third one is parallel operation of a two dissimilar single phase transformer of a different kVA and determination of load sharing and analytical verification given the short circuit test data. And the fourth experiment will be polarity test and connection of a three single phase transformer in star delta, delta delta, and star VV connection, and determination of efficiency and regulation under a balanced resistive load. And fifth experiment is related with the Scott connection with the balanced and unbalanced loads. The next followed by the remaining experiments are the separation of hysteresis and eddy current losses in a single phase transformer. And this completes the transformer part, and related with the generator, that is we are going to relate with the alternator experiments, that is the voltage regulation of an alternator by EMF and MMF methods, voltage regulation of an alternator by ZPF method, and also the slip test, that is the measurement of a direct and quadrature axis reactance and predetermination of a regulation of a salient pole synchronous machines, and also the performance of the synchronous generator connected to infinite bus under a constant power and variable excitation and vice versa. And also it covers the power angle curve of a synchronous generator. Now let's move on with the cycle of experiments. The first experiment which I'm going to conduct is the open circuit and a short circuit test on a single phase step up or a step down transformer and predetermination of efficiency and regulation and the calculation of parameters of a equivalent circuit. So the first four experiments will be related with the transformer itself. Now let's move on with the first experiment, that is open circuit and short circuit test on a single phase transformer. So what is the aim of this experiment is we need to conduct the open circuit and short circuit tests on a given single phase transformer and to predetermine its efficiency, regulation and constants of the equivalent circuit. So let us see what are the apparatus which we require to conduct this test. Before that, let me brief about why do you conduct this experiment. See, whenever we would like to find out the behavior of any device, right? Under certain operating conditions, we need to predetermine its parameters. What are those parameters? It can be efficiency, regulation, and other constant parameters. So here, I'm going to perform the test on a single phase transformer. So to find out the performance characteristics of a transformer, we need to conduct two tests. One is open circuit test and a short circuit test. Open circuit test is also called as no load test. The purpose of this conducting this test is to determine the core or iron or excitation losses and no load current I0, and thereby the shunt branch parameters like R0 and X0 of an equivalent circuit. So in this test, one of the winding will be kept open circuited and the rated voltage at the rated frequency will be applied. to the other windings. Here we have to make ensure that in case of the measurements are made on the HV side, the voltage applied to that winding. But in case the measurements are made on the HV side, the voltage which is required to be applied, it would be inconveniently large. So here the current I naught, it would be inconveniently very small. So that is why the primary side, we are keeping it as the HV, the voltage, the high voltage side, and the secondary side, that is LV, that will be kept open. And short circuit test is also called to be as a impedance test. Here, the purpose of this test is to determine the full load copper losses and equivalent resistances, equivalent reactance, which is referred to the primary side or the metering side. So here, with the help of the auto transformer, a very low voltage will be applied to the primary side till the ammeter is going to reach the rated current. So in the both of the test, we require the instruments like the ammeter, voltmeter, and also the wattmeter. So the next question arises, what type of the wattmeter do we require? We require the UPF wattmeter and also the LPF wattmeter. Since in the OC circuit, we are keeping the one of the side of the transformer as open. So there will be a very low current which will flow through it. So therefore, we require it is a no load. So the current will be quite low. So a low power factor wattmeter will be preferred for conducting the OC test. And in the case of the short circuit test, the other part of a winding will be shorted. Due to this reason, we require the unity power factor type of the wattmeter. So let me list out the apparatus. The ammeter which we are using, that is 0 to 1 ampere. This is for the OC test, and 0 to 10 ampere, we require it for the SC test. 0 to 30 volts, this is also we require it for the SC test. 0 to 300, we require it for the OC test. LPF wattmeter, this is required for the OC test, and UPF wattmeter is required for the SC test. And the type of the device which we are using is a single phase transformer, which is a rating of a 2 kVA. Now let's move on with the circuit diagram. So in the OC test, as here we need to connect the transformer. This is the transformer to which we are going to conduct a test. The primary of this transformer is connected to the wattmeter, which is in series with the ammeter, and the ammeter is connected in series with the supply. So this supply, which you are going to get it from the auto transformer. So this auto transformer is going to provide a supply to these meters, and also the voltmeter will be connected across this winding of the auto transformer, and the secondary side will be open circuited. So here, what will be the procedure? See, in this, make ensure that the open circuit the secondary winding, and here ensure that the auto transformer, this is an auto transformer which is in 0 voltage position. Close the supply switch. Vary the auto transformer till the rated voltage, that is 230 volt, is applied to the primary winding. But when we are going to conduct this test, here on the bed, we will not be provided with the 230. Instead, we are going to make use of a 50% of a tapping, which will lead to 115 volts. Okay, so we have to prefer for the 115 volt at the primary side. Then note down the readings of the no load current, that is denoted as I naught C from the ammeter, and no load voltage, that is V naught C from the voltmeter, and the no load power factor, no load power, that is WOC from the wattmeter. Then after getting all these readings, before you take up the wattmeter reading, we should remember the K constant. So the K constant is nothing but the V into I divided by V into I into cos phi divided by full scale reading. So to the voltage terminal, to which voltage we have preferred in the wattmeter, and the current what we have connected, the plate, whether it is connected in the series or the parallel, depending on that. Then power factor. If it is a low power factor, it will be obviously 0.2. Otherwise, UPF means it is 1, divided by the full scale reading of the wattmeter. So this K constant will be multiplied with the reading which is read on the wattmeter. After taking down this reading, we have to bring back the auto transformer to the 0 position and open the supply switch. The next question arises, this is what we have to tabulate in the tabular column. So as I told you, we are going to provide the 150 volt. Okay. Then coming to this is about the open circuit test. Now coming to the short circuit test. In the short circuit test, the same supply will be, the same circuit will be followed. The only the difference is this will be short circuited. And here, we will prefer on the primary side, on this side, we will be having the HV voltage, and on the secondary, it will be the LV side. Okay. So here again, we need to follow the procedure, that is make ensure the short circuit the secondary winding, and replace this wattmeter with the unity power factor wattmeter, and make ensure the auto transformer is in 0 voltage position. Close the supply switch, then vary the auto transformer till the rated voltage current flows through the primary winding. Then note down the readings of the short circuit current, that is ISC, from the ammeter A, and the short circuit voltage, that is VSC, from the voltmeter, and the short circuit power, that is WSC, from the wattmeter. So again, we need to find out the K constant for this wattmeter, and we need to take down the wattmeter reading. Then bring back the auto transformer to the 0 position and open the supply switch. Here the question arises, what will be the rated current, or what current you have to change the auto transformer? You need to vary the auto transformer. By default, there is a formula which is there from the theory part, that is the kVA is equal to V into I divided by 1000. The same formula, you need to apply it here to find out the current ISC, that is kVA into 10 power of 3 divided by 230 volts. So it will lead to 8.7 amperes. So we have to apply 8.7 amperes. So the related the voltage we have and the outing this we have to this completes your short circuit test. Now we need to do the further calculations to plot the graph of the efficiency, and as well we have to determine the regulation. So we have obtained the core loss from the OC test and the full load copper loss from the short circuit test. Now let's move on with what will be the formula related with the efficiency. So efficiency is given by output by input into 100, or it can be given by output divided by output plus losses into 100. Then what is the output? That is X into kVA rating into 10 power of 3 into cos phi divided by X into kVA into 10 power of 3 into cos phi plus W naught C plus X square into WSC into 100. Okay. So what is X? X will be the fraction of the load, right? So here we need to calculate for the different fractions like 1 by 4, 1/4 of load, half of the load, 3 by 4 and 1. Here in this experiment, you are not nowhere applying a load. So this is without loading, you are conducting the test for a single phase transformer. So with the help of the losses itself, we are going to calculate it with the different loads, that is manipulating in the formula itself, that is 1/4. X as denoted for a 1/4, half of it, 3/4 and 1. Then here our aim is we have to find out the efficiencies of the input. So what will be the input and what will be the output? So as you all know that this output, we have to calculate it in the watts. Before that, you should have an example. What is a power factor? Power factor is nothing but defined as kilowatt divided by kVA. Okay. So I want kilowatt. So therefore, kVA into cos phi. kVA into cos phi. kVA can be obtained by multiplying the x fraction multiplied by the rated kVA. Rated kVA is nothing but 2 kVA of a transformer. We are taking one example, that is 0.6. For this power factor we are calculating. Like that, you need to calculate for the different fractions like 0.4, 0.8, 1, like that. Okay. So that you can plot the graph. Now here, this is how the output can be obtained in terms of the watts. Then, this will be the output. What about the losses? The losses in the copper loss is a variable loss. So this will be taken as x square times of WAC. So each time we have to multiply with the fraction of a load. And W0C is the iron loss. That is these two losses will be appearing in the efficiency formula. Okay. Then this will be the total loss. Okay. So as you all know that the efficiency is output by the input. Input can be written as output plus losses. Okay. Input can be written as output plus losses. So here what you can observe, this input will be nothing but the output which is obtained plus the losses of these two. Okay. So here after that you can calculate the efficiency for the different trials. We need to calculate it. Then like that we need to solve for the different ratings. Further, we need to move on with the regulation. So in the regulation, you can obtain by the formula I2 into R02 into cos phi plus or minus I2 into X02 sin phi divided by V2 into 100. So here, the I2 will be the rated current and V2 will be the 230 volts. And the power factor, we need to assume it as 0, 0 0.2, 0 0.4, 0 0.6, 0 0.8 and 1. So here the plus which is indicating that is for the lagging power factor and minus is indicating for the leading power factor. So the next question arises, where do you get this R02? So there is a formula related with the R02 and X02 for the and SC test. Let's move on with that. So here the R02 is nothing but we can write it as this is the parameter which is referred to your the secondary. So here it can be obtained as the x square multiplied with the, it's actually the k square multiplied with the R01. So k is nothing but it is a transformation ratio. That is, it is 1:1. So it will be considered as a 1. So before that we have to find out what is R01. R01 is WAC divided by IAC square. So we need to calculate with the values what we have obtained at the OC test and SC test. Sorry, SC test. Then Z01 can be obtained by VAC divided by IAC. Once you get this value, then only we can find out the X01. So X01 can be given as square root of Z01 square minus R01 square. So once we solve this, we can solve in the regulation. So that regulation formula we have to reply and we need to solve it. Once you get that for a different various values, we can plot this graph, that is the power factor for the lagging case and for the leading case with respect to the different power factors, we can obtain the regulation. Further, we can also write down the equivalent circuit which is there on which is referred to your the secondary side. So that is R02 and X02. So the corresponding values you can find out. So these two values can be obtained by your the short circuit test. What about these two? This is a shunt circuit. So this can be branch shunt circuit values can be obtained by the open circuit test. So for this also there is some formula for the R0. So R0 can be obtained by using a formula V0 divided by IW. So here VOC can be obtained from your OC test, and the IW is nothing but it is a component. So let me call that a component is nothing but IW working component, that is I0 into cos psi 0. Similarly, the X naught can be obtained by V naught divided by I mu. So how to find, this is a magnetizing component. So I mu can be written as I naught into sine phi naught. So this completes your finding the equivalent circuit of a transformer. So this completes the experiment. So further, the result will be the open circuit and short circuit tests on the given single phase transformer is conducted, and its efficiency regulation is determined for a given load and the power factor. The equivalent circuit constants are determined. Thank you for watching this video.